Thank you so much for this opportunity. So this is the course of classical dynamics for 3 hours. So in 3 hours, complete covering of classical dynamics is a bit difficult. So rather, instead of introducing all the techniques of classical dynamics, what I want to present in this 3 hours is that physics, the study of physics is fun. It's really, very interesting thing. It has lots of realistic applications. Many things that we see around us are governed by classical dynamics. So this is the feeling I want to make to you. So then rest of the thing is go and do your own homework if you want to be a master in this one. Okay. So you might have already heard about Newton's first, second and third law. By the way, do you know what is actually physics? Can somebody explain what is physics?
Some of the people from the want to give a definition. What's about physics? B.
How to explain the nature?
Yes, exactly. It's the study of nature. So it's study how nature is governing, right? And the first topic, you might have already seen many things are there in physics like electrodynamics and mathematical tools like partial differential equations, then group theory, symmetries are there. And classical mechanics is the first branch of physics which is developed, it's the first branch of physics which is developed. And Newton is the one to really very cleverly developed how the nature is working. So you know 3 laws of physics, right? Newton's first law of 3 laws of mechanics. Newton's first law, Newton's second law, Newton's third law. These three things you know already, right? Is there anyone you can tell openly? I can say what it is, what they are. So it seems everyone knows it, right? Okay. So what Newton's tried to think about is how the particle is moving, how particles are interacting with other particles. So these are the things he is trying to do it, and I will directly write the Newton's second law. This is the first thing you might I am going to write here, and this is the second law of Newton, which you might have seen in this form. Force is equal to mass times the acceleration. So acceleration is nothing but the second derivative of the position. So this is the definition of acceleration. All right. So maybe this r is my coordinate. Sometimes some people use x. So this is just a coordinate, just a position of the particle, and its first derivative with respect to time is velocity, and second derivative is acceleration.
Make it different between R and V.
R and V, yes. Okay. Okay. Yes, R and V. Okay, I will try to be more clear. No. Okay. So have you heard about the object P, momentum, linear momentum? Right? So linear momentum P is nothing but m times V. So I put this arrow here, arrowhead, it denotes that vector. So you might have seen already this vector in Pradeep's class. All right. So this is linear momentum. What is the idea of linear momentum? Linear momentum, we say that, oh, this guy has lots of momentum. So he has lots of, we always say that he has lots of momentum. It depends on mass and velocity. This is not but velocity. velocity which is defined to be like this. And the force is nothing but the first derivative of momentum, and in this point I consider that m is actually a constant, it is not a function of time. So you can actually derive this, these two things are equal. Now the goal of classical mechanics is to use this idea and integrate the equation, because it has a two derivative, integrate with appropriate initial conditions and find out the path of a particle governed by these rules. Okay, so everything is clear. So the idea of classical mechanics is to find the path of the object which is passing in the system we are considering. Now and this is linear momentum, and in the group theory class there were explanation of symmetries, group and conservation, right? So conservation means something is not changed, okay, so that is called conservation. So to get the idea of a linear momentum, I want to make some demonstration. So maybe you people want to, can you see this tabletop? So what I have is two coin. One is 10 baht coin. I don't know what is how much baht is this? 50? Okay, so it's half baht. Okay. Okay, so of course you can see the size and weight is different. This is weighting more and this is this weight less. Okay. So what I want to do is I will initiate some I will give some force. So this will carry a momentum. Okay. So it was initially at zero motion, so it was not moving. So I will do a initiation. So initiation is this force. The force, I will apply the force. So there will be a change in momentum. So initially it had a, it's not moving. So velocity which is the time derivative of the position is 0. So now I apply a force with my hand, and so that it has a time derivative of the momenta, and it will carry this momenta and hit this this smaller one. Okay. So this is what I want to see it, and watch carefully. Notice this small coin. Okay. This is what I am going to do. So notice how fast this is going, how fast the smaller one is going. See, this is moving up to here. So let me mark. Okay, so let me begin again. So this is my starting point. This is my second thing. We'll mark it where this is ending up. So this end up here. Now I am going to reverse it. So I am going to reverse. I am going to hit this thing with the larger one. You see that it didn't move almost. Why this happened? What is the reason behind it? Can you explain why it didn't move far away, or why?
50 star have less value than 10
Yes, exactly. less mass. Okay, so this is what I am going to. So this is. Yeah, exactly. So I gave a momentum to 10 baht coin, and which is equal to mass of the 10 baht, a velocity of 10 baht, I call it. Okay, so 10, it's not, oh sorry, mass is not vector. Okay, this is vector, and what I am going to do is I transfer this to this half baht coin. So it will have a half and a velocity like this, and these two are equal. So I'm completely transferring, and this is called conservation of momentum. So all the momentum will be transferred to the other one. Okay. So and also you should also at this point notice that the vector has a meaning here. If I hit with an angle will also be a then there is a directional dependency. So I try to be as direct as possible. So you see this one, if so since momentum is conserved, whatever I give, it will transfer to the other one. So P tan equal to P half. So, which means that m 10 v 10 equal to m half, and of course m 10 is larger than m half. So, only way to balance this equation is to make this half velocity of the half coin higher. Does it make sense? So, that is the reason why the smaller coin traveled longer, because it got a higher velocity. So, does this make sense? Okay. Now, along this conservation of this linear momentum, let me try another experiment here. I hope it will work. So, what I want to do here is that, so here everything is identical coin. So, I have 1, 2, 3, 4, 5, 6 coin. So, I separated 1/7 coin here. Now, I am going to hit, I am going to give a momentum to this one, and the momentum will transfer, and let us see what is going on. So, this is going to happen here. So, I am going to hit, you see this got separated. So, the momentum got transferred, everything and it moved. So, if I have 2 coins, so that means I am adding mass. Suppose I do like this, what will happen? What do you expect to happen? 2 coins will separate. So, let us see the 2 coins got separated. So, this is actually the idea of conservation of momentum. So, what I want to show here is that whatever you see around, this is the simplest thing what I can show. Maybe there may be much more simpler thing, but what I am saying is that this is just daily activity, right? When you go, there will be collision between these coins. Then that collision is not important, but there will be much more bigger collision which are important. Suppose how the river is flowing, how earth is moving. Okay. So, this is about the linear momentum, and now having defined linear momentum for single particles, let me move on to angular momentum. So, this is the statement of second Newton, and when this when the force is 0, the momentum is conserved. So, these things will be coming, conservation and symmetries will be covered later on. Now, let us come to the angular momentum part. Angular momentum is defined to be the quantity L, is nothing but R cross P. Okay. So, R cross P. So, let me suppose okay, suppose what is the system you want to, suppose I have a thread and I have a bead, and if at the end of the thread, and if I do this kind of activity, so it's a kind of rotational motion, right? So, suppose I have a, this is my finger, let us say this is my, I am not very good artist. So, this is my finger, and if I, so this is my hand, and if I put a bead on here, so this rotation, I can make this rotation, right? So, this is R, and this will have a momentum when I do this. If it has a velocity, this will carry a momentum. Ah, exactly this one. Suppose if I do this, I think I will not break it. Okay. So, you see this one, this kind of motion. So, this will have a angular momentum which is conserved. I will show you what it mean by conservation. So, you see that this is the angular momentum. So, I am applying a little bit of force to have this momentum, and it has a length r. So, the angular momentum is r cross p. Okay. So, then there will be a force, thank you, there will be a force which is called torque, rotational force. So, I call it as tau, which can be defined to be r cross f. Okay. So, now if you apply this, I mean, if you can, okay, so what I'm going to do is that I'm going to make a cross product of R on this this equation. What you get is R cross F equal to R cross P dot. So this become tau, this become L dot. So this is the rotational version of Newton's second law. Okay. Now this is also like linear momentum. This can be conserved in a motion which I showed you, and also this is in the group theory class you have heard that Newton understood that, or Newton said the laws that we are governing here is also applicable to celestial bodies. Suppose, so what I mean is that the same rule applies to here. So I show this motion, rotational motion, right? And is similar if we have an object here. So I call this a sun. So let me draw a sun. And this is our earth, and this is rotating along this, on this, around this sun. Okay, so this, where this is happening in the sky, right? And what I showed you is happening here inside this room. So whatever the rule applied here will also be applied here. So this was a very, very paradigm shift in the understanding of our universe at that time. So for the demonstration of angular momentum, yes. Yeah, see this. Yeah. So to understand what is conservation of angular momentum, so can somebody come here?
She said she wants to.
Who is more sleepy here? Okay. So you can sit here. Okay. So what I want you to do is you keep these two bottles like this, and when you can give some signal so that she stretches like this.
I think give signal.
Okay. Then immediately you ask her to come back.
Okay.
So what I want to show is that when she stretches, the rotation will go slower.
Oh, I feel guilty now.
Okay, so keep it like this. So can you raise your leg a little bit?
Open your arms.
No, keep it like this. Okay. Oh, I hope this will work. Okay. So I'm going to rotate it. So stretch it. Come close. Now do it. Okay, you don't notice any much difference. Okay, so I will make it a bit fast.
1 2 3 แล้วก็เดี๋ยวดูสัญญาณอาจารย์ว่าการอยู่เมื่อไหร่นะ 1 2 3 1 2 3 okay
Okay.
a little faster
Okay.
What?
Close. Do you notice?
Okay.
Okay, she's having dizziness now.
Reversely, so it's a reverse transformation.
So what? She's fine.
We bully student here.
Okay. So what you might have noticed that when she stretches her arms, it's getting slower, right? So when she stretches her arms, it gets slower. So can one of you come? Can you have a? Okay. So first you stretch like this. Okay, sit here, and you can. Now you can keep your legs here. Okay. And keep arms like this. Okay, I hope I don't hit you. Okay, so can somebody ask him to close? Yeah, when asked to close, you should do like this. Okay? Then you will see that this rotation will be faster. Okay. Okay. Is it become faster? So okay, so first you do it again, and yeah, okay, okay. Okay, so do you notice some changes? Do you notice some change? What is the change? The speed of rotation changes according to the length of the arm. Like when he close, it becomes faster. When he stretch, it becomes slower. So why this is happening? Again, if you look at this equation of, okay, you can go back now.
Next one, get the next one.
Yes, yes. So yeah. So you see that this L okay, so I am going to divide the angular momentum into two parts. One is when he was closed his arms. At that time, suppose this is him and he was rotating. Okay, so okay, let me draw like this. So when his arms were like this, so the angular momentum, the rotation is happening along this along this path, right? So the distance r is almost like this. When he stretches, what happens is that, so the rotation was happening along this arm. So this r is higher than this r. So when r is smaller, to conserve angular momentum, only possibility is to increase p. So when p increases, he moves faster. That's what I want to demonstrate before you. Okay, so this is the idea of angular momentum. Now the next thing we want to do is energy. Okay, so to do energy, what kind of energy do you know about? Kinetic energy, yes. So kinetic energy T equal to 1 by 2 m r dot product of r dot. So this is r naught v, okay, r dot. And if we take a time derivative of this quantity, it is nothing but p dot r dot, which is but f comma r. So when you do an activity, when you start, suppose an object start moving, suppose a car starts moving, it will have a kinetic energy at some velocity, and at the time passes, the car will slow down, then it will have another kinetic energy at time. So what I want is a time 1, at time 1, at time 2, an object start moving with a kinetic energy at time 1, and another at another time t2, it start slowing down. Okay, so it will have a different kinetic energy at time 2. So the difference between these two things can be computed as T2 minus T1, kinetic energy at T2 minus kinetic energy at T1, which is nothing but integral of this object from T1 to T2. Then this object, this dt by kinetic energy, the time derivative of kinetic energy which I wrote here can be replaced here. So, T1, T2 is F r dot dt, and again integrating over this r dot, this is r dot which is dr by dt. I can cancel this dt, then this integral changes to like this, from r1 to r2. So, r1 is the position where the car is at time 1, and r2 is the position of the car at time t2, becomes f dot dr. Have you seen this object f dot dr? F dot r, have you seen before? So, this is called work done. So, all this I am rushing through this concept. So, starting from linear momentum, angular momentum, kinetic energy, work done, then we can move to the much more formal formulation of classical dynamics. Okay. So, then suppose we have a motion of a particle which is on a closed path. So, closed path means an object here start from this point and he make this kind of rotational, this kind of a closed path motion. Okay. So, then this R1 and R2 are same. Do you agree? Okay. So, he starts from R1, then he goes to this point, and again he comes back here to the same position. This kind of is what it starts from R and it ends at R2. Now, R1 and R2 are same. So, then this integral becomes a closed integral, right? Have you seen this object, closed integral? Okay. Closed integral f dot dr. Okay. So, there are particular kind of force like the force on this that is governing in the solar system, and which is called gravitational force, and also electrostatic force. And these forces are very peculiar because on a closed path this object will be 0. So, these forces are called conservative force. So, what I am introducing a new concept is called conservative force, and in this I am going to wrap these points. So, in this conservative force, if this is 0, I can write this, you might have learned Stokes theorem, right? From Stokes theorem I can write to be like this. If I have a closed integral going to 0, this quantity actually is curl of f becomes 0. Okay. Now, from a peculiar property of this space, we can write the force to be negative gradient of a potential. Have you seen this before? Yes. So, do you know what is potential energy? Can anyone demonstrate what is potential energy? What is potential energy? Can anyone tell what is potential energy? Have you heard about gravitational potential energy? MGH. MGH. G is nothing but acceleration of the gravitation, right? It's the earth when we are here. If we are on the moon, then the G will be changing, right? And mass is the object's mass, and h is the height. And suppose we have a scenario like this. So, this is a, suppose this is a building and this is the ground, okay, we have some here, and a person stand here and he drops a stone. He keeps a stone like this, okay. So, this is the H1, and a guy, another guy here, he also has a stone here, same mass, same identical mass stone, and this is H2. Who will have more potential energy? I mean, which stone will have more potential energy? This one? This one, okay. So that means you already know it, what is potential energy. It depends on the height of the object from the reference here. So, to demonstrate again, so if you have more potential, he will have more force to do it, because that is the relation here, okay. Okay, so to demonstrate it, you can see this, I build this thing. So, what I want to do is here, I will drop the chalk to this object with two different height, and you will see which will have more force. Okay, suppose I drop it like this. See, it got broken, but it didn't, it broken like this. So, I am going to do the same with same chalk with a different height. Let us see what will happen. You see, it already broke to inside. So, this is the difference of what mean by potential energy. So, higher potential will be with the object which have longer distance from the reference. So, this is the concept of potential. Potential is something, some kind of energy which an object possesses at rest. Kinetic energy is the energy possessed by an object when it is moving. Okay. So, what I showed here is the overview of Newtonian mechanics. Okay. So let us talk about this force, conservative force. Now I convey the idea of kinetic energy and potential energy. Now here what we did is this, we had previously we had this integral here. The difference between the kinetic energy was written to be in this form. At time 2 minus kinetic energy at time 1 is equal to R1 R2 F dot dr. Okay. Now the F is when the force is conservative, we can substitute this object here. So we will have minus potential dot dr. This del operator is partial derivative with respect to r, So then I can write this is equal to potential at time 2 plus potential at time 1. Now we can rearrange these terms at time 1 and time 2, which is plus T1 is equal to T2. So what I did is I replaced F with conservative force, and I made an integration from 2 points R1 and R2. So that is minus V1 minus v at time 2 plus v at time 1. Then what I did is I brought this v to this side and t to this side. So I have this this relation. So T plus V, kinetic energy plus potential energy is the total energy possessed by that object. So I said that kinetic energy is the energy of a moving body, potential energy is the energy of a at the time it is static. It will and as you can see that this is the total energy of a body, E1 at time 1, E2 at time 2, and you see that E1 equal to E2 after having a motion of a conservative force. So this says that energy is conserved in this motion. In conservative force, energy will be conserved, and this is called Hamiltonian in more refined language. So now this is all about point particle. So this is the thing you might have studied inside Newton's equation, Newton's classical mechanics. Classical mechanics is described by Newton. So he starts from position, velocity, acceleration, then he introduced 3 laws of motion. Then we will have the idea of linear momentum and its conservation, angular momentum, its conservation, and the idea of energy. And in the energy also we have a potential energy, kinetic energy, and conservative force. And in conservative force I showed that energy is so this is about single particle. Okay, so and I said at the beginning of the class that physics is about the realistic study of nature, the system what we see around, and what we see interactions and so on. So then okay, this formulation works for single particle, but to make an application to realistic system we need to enhance this to multiple bodies, right? We need to so there will be sometimes there will be scenarios like so this is one scenario, single particle. You can consider it as point particle mechanics. There is one body here and another body here. It has same interaction, which is gravitational interaction in between. But there can be scenarios, but there are many scenarios, like there are many particles around and all of them will have interaction among all the particles. Okay, this becomes much more complicated now. Now each of these particles has to assign a coordinate, and we have to develop the same Newtonian mechanics, same laws, same concept like linear momentum, angular momentum, and so on to the whole particle. So this is what I am going to do now. So what I will do is this, starting from this F. So suppose we have a system like this. Okay, so there are 5 particles, right? So for one particle I said okay, force is rate of change of momentum. Now what I am going to do here is that I assign I. So I can be 1 2 3 4 5, 1 2 3 4 5. Okay, so equal I. So this is how we are going to formulate for multiple system. Okay. Now what is the total force here? So total force Fi can be a force. Do you get this point? So it has an interaction with other one. So let me assign 1 2 3 4 5. So this one, particle 1 is having a force with particle 2. This one has a force has a force with the particle 3, 4 and 5. Okay, so then this can be written like plus external. So now I am going to drop this this arrow head from in this description. I think F R V A P, all these are vector quantities. All of them will have an arrow ahead to indicate that these are vectors. So now I am going to skip that part. So why I wrote this F external? Suppose if there is a some other body here, and this will have an external force on this one. So I am going to, this is the external force I am considering. Okay. Now what is the total mass of this system? I mean total force of the system. So it is the sum over all Fi. This becomes sum I with j not equal to I. I external. So this will also have a force with an interaction with the other each particle. So is this idea clear? So what I did is, to understand the total force of the system, I made a sum over of this one. Why j is not equal to I? It's because it will not have a force with on its own. So like, yeah, I will do it with a 4 particle system. I will try to expand it and show you. So total force, this becomes Ij plus Fji external. Okay, so I wrote this thing in this form. So why let's say I have a 4 particle system. So 1, 2, 3, 4, and one will have interaction with these 3, 2 will have interaction with these 3, and 4 will have interaction with these 3 things. So let me write this equation like Fi is given to be F sigma Fij plus Fexti. So this is for the ith particle. Let's say it's for particle 1. So F1 is sigma of F1, j is 2, okay, and plus F13, F14 plus Fi external. Now I want to sum this one. I will have F2 like this. F2 is sigma F21, F23, F24 plus F2 external, and also for F3, F31, F32, F34, F3 external, and also I will have for fourth one F4, 41, 42, 43, 4 external. Now I have to sum all over this thing 1, 2, 3, 4, right? And here you see that I have F12 and I have F21. So what is mean by F12 and F21? Newton's third law comes, right? F12 is, so if there is exactly. So body number 1, a particle number 1, particle number 2, it will have a force on this direction F, I say it as F12. This will also feel a force that is F21, and by Newton's third law it is equal and opposite, right. So then when I sum it, when I change it the index, it will have it will cancel all these terms, right, and what remains will be the external will be summed over, all other things will be cancelled due to Newton's third law. Okay. So what I want to write here is that F is F external I. Okay. So this is what I want to say. So in this multiple system, and if we have an external body acting, this whole thing will act as one unit, okay, because all the internal thing will be cancelled over because of Newton's third law. So like that we can have linear momentum, angular momentum, and energy for multiple system, and so now the time is almost I'm going to finish it. So there is 10 more minutes, right? Okay. Okay. So these things are very familiar for you. I'm not going to do the multiple system now. So what I want to show here is that where are the physics being applied. Okay. So for that I will show some videos which is available in YouTube, and you can see that these things comes from standard sports to celestial mechanics. Okay, so I want to show you some videos where these things are applied. So do you people like sports? How many of you like sports? No one. Basketball. Then it's okay, it's fine. Yeah, I will show this. So have you seen cricket? Have you seen cricket? No. And here you can see that in the sports there are lots of physics involved. So can you try to figure it out? Where are the physics involved? You see how the ball is moving. So what the bowler is doing some technique such that he is making I mean the such that the motion of the ball is different than expected. So, and this is a kind of application of physics. Okay. So now next, maybe you are more familiar with badminton, right? This you can relate very well. So this is exactly the transfer of momentum. When a person smash, it's really a transfer of momentum. Okay. So he jump and smash, that means there is a transfer of momentum happening, so that we can win over the other guy. Do you understand? So if you hit so hard, the hardness, I mean the way you swing the bat, the racket, transfer the momentum to the shuttlecock such that he is not able to cope up with the speed. So that's the trick being applied here. So everything is on the physics. Okay. Finally, you can also see this very fantastic football yeah. So this you will be very much maybe you might have already seen this before. You see how this kick is happening. I'm sorry. You see this how kick is happening. Can you figure out the physics here? You look at the trajectory of that ball. So I'm just I'm just showing some interesting facts about learning physics. It's a goal, and you see the replay. It is it's called the banana kick. So it will move on the shape of a banana. You see that it is moving. It's very unpredictable for the people who are trying to block that ball. Okay. So what I want to say is that these are all in all place you can find the the laws of physics there. Okay, and what after learning this, what physicists really do it, they want to understand the nature. They want to understand how the world is really working, how the solar system is working. Maybe even you can apply to your sports. And until now that you can see that this is a animation of solar system. So animation of solar systems, you see that the object closer to the sun is moving faster. So there are something behind, some physics behind, and this system is holding very stable. If it is not stable enough, we will not be here to discuss these things. Okay, so then the question is why it is so stable here, why it is like acting like this. So all things are answered by Newton with some kind of very small correction which is done by Einstein. And finally, I want to show one more thing, that the realistic world is very complicated. So this is the animation done by a team to study the large scale structure in the universe. So how the structures are formed beyond solar system, beyond galaxies. And you can see that here all these these are called filaments. These are very complicated simulation, and you can see that these bright things are considered to be object, and on cosmological time these are evolving, and it has a rich complicated dynamics with Newtonian approximation which works very well. So what I want to say is that when we discuss all these mathematical formulations of physics with very boring things, this is actually very beautiful, very appreciable to understand the nature. Okay, so with this I'm going to stop my first lecture. So next time it's going to be all these things can be restructured in a different language. You might have already heard about Lagrange. So we will introduce Lagrangian dynamics, and it's there are many appreciable points to that way of approaching particle dynamics. Okay, thank you. Okay, so what I did in the last class is just an overview of what is really classical mechanics is about, developed by Newton. And there we saw that he started from coordinates, then velocity, acceleration. Then he started defining three laws of motion. Then force, momentum, linear momentum, angular momentum, energy, then conservation force, and so on. And I elevated those things to multiple systems, right? And I showed that in the video that all the things what we see around depends on this classical dynamics, okay? And the system we want to play with is multiple systems. And I show, for example, the motion of planets around sun, and also motion of structures in the universe. Okay. So now again I want to introduce these concepts now today, like coordinates, degrees of freedom, least action, constraints, generalized coordinate. And finally I will do simple harmonic oscillator. Yes, with Newtonian dynamics, Newtonian formulation, and what Lagrange, other formulation what I am going to talk about. And you don't need to write. If you find that copying from board is making you difficult in understanding, stop doing that. What I want to say is that listen to this and try to follow my my words and what I wrote in the board. And after that, these kind of things are online. You can download it, read it. After that, then still you can contact it. So no, don't need to copy it.
He said that means you don't need to teach because he can download it.
Okay, so the coordinate usually we are living in a 3 dimension. This part is very clear, right? So we have x, y, and z direction, and this is called coordinate system. Around the origin we point a system, a particle there, and we say this is r, okay, with a vector, and r is nothing but square root of x square plus y square plus z square. You know this part, right? Anybody not familiar about this one? Okay, you all know about this. What is r is actually the magnitude r. Now suppose a particle is here. Okay, a particle, this particle. Are you feeling sleepy? No, okay. So suppose I keep this chalk, okay, and where do you want to put the coordinates? Origin. There is one coordinate, looks like a coordinate, right? This is x, y, and z direction.
Yeah. What is this? It's A and B.
Okay. So if I keep a particle, in which all direction this can move? Can you tell? In which all direction I can move this particle? Everywhere. So can you be a bit more specific? Yes, translation along which all directions? X direction, y direction, and z direction, right? So if I do this one, it's really a combination of these 3 movements, some combination of these 3 directions. So essentially this particle can move in 3 directions. So this is called degree of freedom. It has a freedom to move in x, y, and z direction. So how many x, y, and z? So it has 3 degree of freedom. Okay? So this is clear?
Yeah.
And all the other motion is a combination of x, y, and z. Right. Suppose suppose I take this, I don't know whose is this. So I have this bottle, and this is rolling around along this one. It's like it's having this direction, right? This is y direction, and also when it comes here, it is going down. So it is a y direction. Okay, and this is also, this freedom is also there. it's x direction, and this is y direction, and this is actually this is y direction, and this is z direction. This is z, the straight motion is z, down motion is y, and this is x. Okay? So when it is rolling like this randomly, it has all three components. So that's why I said this has three independent way of moving. So it's called this is called degrees of freedom. Suppose I have two particles now, and you said that this already have 3 degree of freedom, and how many this will have? 3. Okay. And when I am considering these two particles in my system of study, this will have 3 and this will have 3. So in total this will add up. So it will have 6 degree of freedom. Okay. Now this idea is very clear, right? So if I have a n number of particles, so when I had one particle, it has 3 degree of freedom. When I had 2, it has 6 degree of freedom. Then it have 3, then 3, 9. Then if I have a n number of particles, then I have 3n degree of freedom. So now this become a complicated system, right? When I have a 10 particle, when I'm going to study a system of 10 particle system which contain 10 particle, so I will have 10 particles here, then it becomes very complicated to study. And for each particle I have to define potential, for each particle I have to define, I have to find the kinetic energy if it is moving, and also I have to see the force interacting in between, like I did the last time. So Lagrangian, his full name is his name is, let me see. No, Euler is a different person, right? Yes, yes. Can you spell it loudly? Yes, you are right. Joseph Louis Lagrange, right? Yes. So he came up with an idea of reformulating the classical mechanics, Newtonian mechanics, in a different language. Okay. So before, so I introduced the concept of coordinates and degree of freedom. Okay. So these things are done. So now you understand coordinates and degree of freedom. Now the part we need to look at is that there is an idea of configuration space. Okay. So equation of motion, we have this F equal to ma is the equation of motion, which can be written as m x double dot, right? So this is a second order equation. Okay. This is a second order equation. What we need to find is the position of this particle and the trajectory of the particle by integrating this equation. So this is what the whole idea of classical mechanics. And when I say x, it can have 3 degree of freedom, and it can be moving in this 3 dimension. So it will have force along x direction, force along y direction, force along z direction, m y double dot, m z double dot. So is it clear? And if I have multiple particles, there will be I here, and then the system become very complicated. So in order to represent this thing, there is another way of doing thing is representing this thing in a different space called configuration space. So configuration space, it depends on the position x and x dot. So if I have a 3 particles moving around in a real physical space, using this configuration space, I can represent the movement of whole system with respect to time in a configuration space with one line, one trajectory in configuration space. So, are you having difficulty in understanding this? So, what I said is that suppose if this is happening, you see this is moving. One moved in this direction, another moved in the other direction, right? I am representing all these things in this space in one line. So, each point in this space is a configuration of this system, of this realistic thing happened. Okay? So, it is a bit difficult to understand, but still what you need to understand, suppose at one point when I throw, at one point it is in this position, it will be represented by one point here. Now, it started moving here, this configuration is here and so on. Okay? So, this is the idea.
So this,
yes.
so this is this configuration space is like a graph between x and x dot.
Yes. Yeah. All right. Now what I want to say is that is about this picture. So, you people already know this picture, right? So, this is a light ray comes, and when it passes through a medium, according to the property of that medium, the trajectory of light changes. So, this is what is drawn here. Even though this this is convex, right? Convex, because of this convex shape, it became like this. Yes. Okay. So, if it were this kind of lens, then it will be doing like this because of the property of this thing. But light itself did not change. So, what is this? What is this idea? So, light always tries to pass through a straight line, right? It is a pass through the straight line, but when it goes through this one, it was not straight line, right? It had a slight bend, right? It had a slight bend. It had a bend. So, instead of why it is straight line? Okay, suppose you want to go to
Why is it a straight line?
why is
Why?
why means question why. Why, not the letter Y, but why.
WHY.
Yes. I thought you got confused. What is a straight line? The straight line is just why it is a straight line. No, not what, why. Why light is passing through a straight line. Okay. Okay. Exactly, yes. So, suppose you want to go to somewhere. Suppose you want to go to where? No, let us take the example of Nakhon Sawan. This is what I am familiar with. Not, yes, Nakhon Sawan, okay. Which path you will take? There are two ways, I know. So, which path you will take? Which path you will follow? There is one path, okay, through this main road, another through the village, you can go to Nakhon Sawan. So, which path would you prefer? Shortest paths. You see? Okay, okay, more fun is another fact, but okay, suppose you don't want to lose energy, but you want to save something, then which one you will prefer? fastest, exactly. So this is what being done here. The light is choosing the same thing. It wants to travel the fastest path. So this idea is this. There is a theorem. It's called Fermat's theorem. So light always chooses extrema. Extrema means it doesn't want to lose. Extrema means it can be. The idea of extrema means it loses minimum energy. It has to spend least amount of its energy. So this is what we also do, right? So yes. So anyone will do this one. So nature follow the same thing.
Can I add?
Yes, sure.
So the light doesn't want to lose energy that much. It's like you travel on the road that you save a lot of gas or petrol. Yeah. Okay.
Yeah.
You don't need to pay much.
Yes, exactly. I mean, why I choose extrema? It need not be shortest. Why I said, okay, extrema has a meaning. I mean, you need to understand extrema has. Suppose this main road is highly traffic, and if you ride your vehicle in a highly traffic way, you will lose more gas, right? Then you will do a longest path which can save your fuel, right? So this is the idea of extrema. Extrema doesn't mean the shortest, but there is an idea of saving something, then you choose that one. Okay? And that's great. So you understood all these ideas. So here also you understood configuration space, and this is called, what I explained just before is called least action principle. Now the question is, what is a particle or a system of particle wants to minimize? So I am going to introduce action. S, which is defined as integral of, so S okay. So just for a notation, I said that P dot equal to F and F so yeah, this is just a notation, don't worry about it. I said P dot is F, okay, so it's a last class, and for multiple particle I have I, index I for each particle, and I can write this conservative force is F is minus gradient of potential of each particle. Now instead of F I replace this one. Now what I am going to do is I introduce a different index like P A equal to minus gradient of V A. So then I said the X, Y, Z. I can write this thing as X1, X2, X3. Then I in terms of short hand notation, I can introduce Xi. Then this I can be A, right, XA. So this is some notation, right. So why I did is Xi, then there will be n particle, then there is n times Xi. So for each particle, for each coordinate, I have one, for another 2, 3, 4. So all of the things are in this A, okay. So A is a collection of all these indexes, and in configuration space it depends on Xa and X dot A. It's just a notation, nothing new things, okay. So this is what I said. So something the system wants to save, that is called action, and action is integral of an object which depends on X. I call that object as L, X and X dot with index A, integral of time from initial time to final time. So, everything is clear. And now the question remains is what is this L, what is this function? Okay, it is a bit tricky to introduce this part. I do not know what happened to the, I mean what was the thought of Lagrange to introduce this one. So, L is kinetic energy minus potential, but the idea is, so there is a minus sign, this is, if it is a total energy it is should be plus, right. Yes. So, energy is something usually something who wants to save, right. Yes. But he has a different quantity L, right. So, it has a minus sign, it is a bit difficult to digest, but this will give the correct results. Now you got the old idea. So, I introduced coordinates, degrees of freedom, configuration space, list action. I said I argued why it is why this always hold, like principle of list action always hold, and I said that this is the quantity what usually a physical system wants to extremize. Now, this is the idea. The next thing is mathematics. Now, how do you do this one? Once you have this, how you are going to proceed to get all the results in Newtonian mechanics. Now, for that let me draw this configuration space. Now, a system, a configuration point, I call it as configuration point in time 1, configuration of time 2, and this system wants to go from this time to the other time. So, it will choose a path. I said it is an extremum. So, extremum could be anything, it need not be straight line, it can depend on many things. So, it can be either this one or this one, anything which is extremum. So, extremum is something that I said that it need to save this one. So, that means a deviation in S, they do not like a deviation in S, they always want to conserve this one. As time evolves, this should not change, I mean the S should not change. So, how do you write this one? Change in S should be 0, right. I do not want to change something, that means that I do not want to change from this position, means my direction should be 0 always, I mean mathematically speaking, right. So, this is what delta, this symbol means change in S is 0. Now, what determines the change in S is actually shift in X, right. Actually this should shift in X, yeah, let me write like this. Shift in X. Now, let me do this shift in X. So, my XA goes to XA plus a small change in XA, and how this change, this is what I am going to do now. So, where will I do? Okay. Okay, so shift in delta S is actually L integral T1 T2 L dt is T2 or Ti T final delta L dt, and now I need to look at change in L. So, it's a, there are mathematical definitions for this. This is just a functional derivative. So, I am not going to these terminologies. So, let me try to do what I want to get. So, delta L is depending on x and x dot, right. So, it is a partial L by partial xa delta xa plus all right. Now you plug this here, it will be IT final. I am going to replace this one. Dt. Now this is a time derivative. This is inside an integral, so I can use the integration by parts rule. So there will be a total derivative and a replacement term. So it will become So what I did, I made an integration by parts, okay. So integration by parts will have a total derivative, time derivative. So this is a time integral, so I can rewrite like this. Do you agree with this term? This term is called boundary term, okay, and the other part is time derivative of this object with a minus sign. When you make a integration by parts, there will be minus sign. And you see that what I am doing here, it has, I said that this is moving through a extremum path. So what I did is that I slightly deviated, tried to deviate this path. The path is on this x and x dot, that is what I did here, right. And I always said that when I do this procedure, initial configuration space and final configuration space should not change. So that means any deviation in x at this point and at this point should be 0. So Tf and Tf deviation should be 0. So this will go 0 at x at the endpoints. So this will be vanishing. And what is remaining is this one. So what I remain is this one. So delta S is dt okay, xa. So this is what I have. And I said that this should be 0. This is delta S and this should be 0. So that means whatever is inside the integral should be vanishing, and that is called Euler-Lagrangian equation. And this is the equation of motion of a system of particles. Get it? Any questions? Any additions? Whatever. So I rewrite this one. This is the equation of motion, dou L by dou xa minus d by dt of dou L by dou a equal to 0 is the equation of motion. Now, what was the equation of motion in Newtonian? Ma, yes, right, x double dot. Then I said that f can be minus gradient of right. So this is p dot equal to minus gradient of v. So I can show that if this is P, d by dt of P, if this is gradient of V, then minus gradient of V, no, minus is not needed. So, yeah, there is minus gradient of V, then this proves that this is exactly Newton's equation of motion. All right. Okay, so now I have to move fast. Now I talked about the motion of particle in all these directions, right? And last time I showed a motion of particle like this. Sorry, I'm taking it again. I said I should not break it. Okay, so I said I can. So, in how many directions this is moving? In x, y, z. X, y. So, if I say this is z direction, this is y direction, and this is x direction, then x, z, right? X, z. So, how many degrees of freedom this will have? But naively, it should be 1, but you see that this is restricted motion, right? I am not allowing to have this motion along the y direction, is not having. Suppose I do this motion. If I do this like this, so it is a plane, right? It doesn't go to, then it will have a, right, 2 degree of freedom. But this is actually happening in a 3-dimensional space. So that means that I am constraining something with this plane. I am constraining. So always this will be present, constraints. So this is the idea of constraint. So okay, so before introducing constraint, I want to show you something. Is that this equation of motion will not change when I change the coordinates. Okay, so this is what I want to show. So I think now you understand all the idea behind the action and its variation. So when I define a new coordinate q a, which depend on, is a function of x a and x dot a, x a's and so on, x1, x2, x3, okay. So that what I do is that I change the coordinate x, I change x into a q with introducing a function. It's a transformation. For example, I have x, right? I can do transformation to r, right? R written in terms of x plus y square plus z. So r is a function of x, y and z. This is what I meant. This r is a function of x, y and z. So from x, y, z, I made a transformation using a function, right? So this is what I am doing here. Now, so if I do this transformation, the equation, the form of this equation remains same. So what you want to do is that, so you have to change this one, and the q dot a is dqa dt is dqa by dxa x dot a plus and also I want this to depend on time as well, plus dqa dt. Okay, using this one you try to make a change like this. Q dot. Yeah, so what you want to do is use this, and x a is a x a function of q a and time. And if you do this, if you now you want to, I want you to do the check, you calculate the same Lagrangian equation of motion and see that you will get this result in the end. Okay, I want you to do this one. Okay. So this understanding is needed to understand what is generalized coordinate. Okay. So I talked about constraint. Now I am, and I said what's happening there. They are laughing. I don't know. What? Okay, okay. Okay.
So they think that your lecture is a music.
Really? Okay. So, and yes. So now you can ask this question: what is the advantage of introducing such a reformulation for Newtonian dynamics? So there are two important reasons. First is Lagrangian equation holds in any coordinate system. This is what I said by words, but you can see that you can, making a general transformation, you can show that this equation hold in this transformed space. So this is like a coordinate invariant thing. Next is that it can accommodate constraints very easily. So this is what I am going to show with a simple harmonic oscillator. And simple harmonic oscillator everyone should be very familiar with, because this is the simplest possible system in which physics can be discussed, like what is happening in a system. So we try to approximate into a simple harmonic oscillator, and whatever the realistic physics is on top of that simple harmonic oscillation, whatever simple harmonic oscillator solution is this sine wave, right? So whatever, even what the power spectrum of universe, you see this thing, this is a modification from simple harmonic oscillator. So each modes is happening because of some process happening to the in the universe. So that's one thing. When you go to quantum field theory, again you will find a simple harmonic oscillator, and this is very essential. So instead of simple harmonic oscillator, a similar system which is called I want to discuss a constraint. So I discuss simple pendulum. Okay. So this is this is a ceiling wall, okay, and this is a simple pendulum is there. So it's doing this one, and this I keep it as y direction, this is x direction, y direction. And can anyone help me in solving this system? using Newtonian mechanics.
I can help you with this already.
Okay, anyway, so let me try to do it. So I have final equation, so I want to arrive at that point. So this simple harmonic oscillator, it depends on how many coordinates. Yes, y and x. And it has a constraint because this cannot go down. So it is restricted to this length L. Length L. Right? This is a constraint. This is a constraint the system is feeling. When I said this system, you said that there is only 1 degree of freedom. It's because this constraint, there is one constraint. Now, I want to find equations of motion. So what I want to is I want to add up all the possible forces acting on this this simple harmonic oscillator. But when I do in the Newtonian terms, this ball is not falling down. It means that something else is pulling up in a balanced way. So I call this as a tension force. It's an external force, constraint force. I call it as T here. So T is going on that direction. Now, how do I solve? Okay. So there should be a force in x direction. There should be a force in y direction. Y direction is really y direction towards the earth. So there will be an mg here, of course. That's it. M is the mass of this board, whatever it is. And now, what is remaining is a tension force, like which is extracting up. So I want to decompose this system into x and y because it is in this direction. So I do what? How I do like this. So this is the way, and the ball is having, and tension is on that direction, and this is theta. And if I decompose the force here, tension force on x and y, so this y I did it, and this angle is equal to angle here, right? And this is tension force is there. I call it as mode, and this I call this as a positive direction downwards, so upwards will be negative direction. So tension is on this direction, right? So on y axis the tension will have this is theta, and this will be cos theta, and this will be sin theta, and t with a minus sign because it's upward along the y. Okay. So on fx I will have t sin theta. This will have a negative cos theta. Now this is m x double dot m y double dot. Okay. Now x and y are there. I already decomposed this one, so theta, this is y direction, positive direction, this is L, so this is L. Change in x is how much? Is in this direction, so it is x, x is L sin theta, right? Y is sin theta cos theta, L cos theta. Okay. Now, yes, sine theta is what? Sine theta is, this sine theta is x over L. So, I can say this is T x over L, okay, T x over L. I do not know if they made a different convention to T. So, actually what you have to write is total force is 0, right. Total force acting on the system is 0. So, then this will be with plus, should be 0. This is total force acting. So, then this x m x double dot will be minus tension sine theta, which is sine theta is x by L. Now, here total force okay. So, I am making some minus sign mistake. I think this should be treated as a positive direction, then everything is fine. In upward direction is positive. So, then this becomes m y double dot is m g minus t y L. This is sine theta. Now, the rest of the step I will explain. Okay, the rest of the steps I will explain. What I want to do is that take this portion x and this portion, do not replace into this these two things. So, this I get the correct answer. These are the two equations of motion here, mg. Okay. So, now what these are the equation of motion in two directions. Okay. This is what make a change of coordinate given by this theta, and L is constant because this length is not changing, but theta will be changing, right. It is oscillating. Now, you find x dot, x double dot, x 2 times time derivative, y double dot, y dot and y double dot, and put it here and arrive at this equation. So, you have to find a linear combination of these two equations. So, one equation multiplied by cos theta, another equation multiplied by sin theta. So, it will take a bit of time. So, I am not doing it to finish this one. So, you go and you can find that there is this equation minus g by L sin theta. So, this is one equation, these are the two other equations in a different coordinate. You see that here actually you have two equations. When you make the coordinate transformation, you only have one equation. So, now it is a bit confusing, like what are the degrees of freedom. So, here comes the idea of generalized coordinates. But before moving to that, so what I want to show here is that this I did by Newtonian right. Now, I can do the same thing. I said Lagrangian dynamics is a reformulation of classical mechanics, right. So, whatever I get here I should be getting it easily, I mean with some advantage with Lagrangian description. So, let me do that one. So, okay. So, I want to do very quickly a talk about constraint. A formal definition of constraint is nothing but constraints are relation between coordinates. Okay, constraints are relation between some coordinates, and there are some different types of constraints, holonomic and non-holonomic constraints. So mostly what we are considering is a holonomic constraint. So because it has a equal relation. So here the constraint is this one, L square equal to x square plus y square. This was the constraint. Okay. Now once we find that, once we see a system, what we want to first find is how many degrees of freedom and how many generalized coordinates are there, okay, and how many constraints are there, how many coordinates are there, and minus number of constraints is the degree of freedom. Okay. So in generalized coordinate you have to find the number of constraints, and number of generalized coordinate minus constraints is the degrees of freedom of that system. So now the L is xa x dot a. Now if you have a constraint f alpha, what you need to do is this one. You change this Lagrangian, which is old Lagrangian plus introducing a Lagrangian multiplier, we call it as Lagrangian multiplier constraint. Okay, so whatever it is. So okay. So now let's do this example and finish it. Okay. So now the L prime for this system is this one. So what is the kinetic? Lagrangian is kinetic minus potential, right? So Lagrangian is L prime is 1 by 2 m x dot square plus 1 by 2 m y dot square. So it has a movement in both direction, x and y direction. Y is a small change, but still it has a, and it has a potential energy, right? Potential energy is minus mgy, mgy. So this is the mistake, the sign problem here you saw here. Now this is L. What is L prime? L prime is L plus the constraint. We have to add the constraint lambda plus L square equal to L. So this is the constraint. So x square plus y square minus L square. So this is the Lagrangian of this constraint system. Now you know how to get this equation of motion, Lagrangian equation of motion. You just vary with respect to x and y. You simply get, so let's vary this action. Okay. So variation with respect to, so this is the, let's compute this one, d by dt of dou L by dou x dot minus dou L by dou xa equal to 0. So this is the equation of motion. So I have x variable and y variable, x variable, y variable, this is a constant, y variable here. So I have everything. Let's do it for x. First let's do it for x. So what is Lx? Okay, so here this a index, this is index a which runs from x and y. Okay, so there will be two equation of motion. We saw the two equation of motion. One is the equation of motion along x, another is equation of along y, okay. So let's do this first part. What is del L by del x? Yes, 2. So this is the total Lagrangian is, okay, so let me rewrite the total Lagrangian. I am having a Lagrangian with constraint. So this L prime is L 1 by 2 m x dot square plus y dot square. This has a dot, this has a dot, plus m g y plus lambda x square plus y square minus L square. So what is the part depending on x? So this 2 lambda x. So now what is depending on x dot? This one, right? So minus d by dt of m x dot, right? And m is a constant, so I can take out. So it become 2 lambda x minus m x double dot. So see, so this lambda can be interpreted as t by L. T by L. Lambda is t by L. 2t by L. All right. So for a norm, okay, 2t by L you can write. Maybe if you add a half here, the 2 will not be there, but you can still keep that 2t by L. So in the, okay, so let me do the other thing. So in y, I will have what? You do this one. What is del L by del y? Let's do this, and yeah, what is this? Del L by del y. What is? Tell me from this. Del L by mg plus 2 lambda, okay, and here 2 lambda y, yes, okay, d by dt of y dot. So you see that this is m, this is g, right, plus 2 lambda y minus m y double dot. See that this 2 lambda again comes like this, t by L, 2 lambda is t by L here, t by L. So everything else is same. So that means this equation and this equation, I got it without any going through the complicated things. You see, to do from Newtonian perspective, I had to say, okay, there is a tension, there is a force.
This is without complicated thing.
I mean, this is much easier. I mean, so there will be systems like much more constrained, like there will be double pendulum. Then how do you define, like, okay, there is its constraint is very difficult to, from the perspective of Newton. So this is what I meant. Okay. Yeah. So yeah. So in these two ways, I did. I showed that these two procedure or these two approaches are same, but there are some advantage when we go through the Lagrangian description. That's why all the physics now follow Lagrangian dynamics. So in terms of Newtonian, it's very difficult. So what you have to do is, in Newtonian idea is that you look at the system, you try to understand what is the total force, and to get the total force you need to carefully look at it. This action principle, you know the principle of least action. From this principle, you know that system wants to minimize something, that's the action which is nothing but integral of L defined to be t minus v. Then you get the equation of motion, that's what I show you. Now I want to make a coordinate transformation, and if you make a coordinate transformation, you will arrive at this equation. So, this is the idea of generalized coordinates here. So, what is the coordinate transformation I want to make is that this L I can change into this Lagrangian is described in x, y, x dot, y dot, right. This is the Lagrangian, right. So, this Lagrangian is x x a x dot, right. So, dots are x dot and y dot, and x a is x and y. Okay. Now, you can rewrite this thing in this way. So, from this coordinate transformation I mentioned before, x equal to L sin theta, y equal to L cos theta, you can rewrite in terms of theta. Then what the Lagrangian together with constraint is this one. So, that is I make a coordinate transformation. So, to a generalized coordinate. So, then L Lagrangian will be 1 by 2 m L square theta dot square plus m g L cos theta. Now, you vary this one, you will end up in this equation. So, with that what I want to say is that coordinates are there, and how to look at degrees of freedom, and what is configuration space, and least action principle, why the Lagrangian and I also introduced Lagrangian, and why Lagrangian has an advantage, because it can accommodate constraints easily, and I showed that simple pendulum motion in both Newtonian description and Lagrangian description, and I showed that it is easy to handle through the Lagrangian description. Okay, so then I end this lecture now. Yes. So, thanks again for coming back for the last lecture. So, last time I introduced very heavy topics like coordinates is simple, it is coming from the first lecture, and degrees of freedom, configuration space, Lagrangian, principle of least action, constraints, generalized coordinate, and I showed the example of simple pendulum. Now, we are moving forward to Noether's theorem and symmetries, and if the time allows, I will also cover Hamiltonian. It is a different formalism of classical dynamics. So, why I am moving in such a fast manner? It is because when you go back to your university, and you will start learning more rigorously what are these in a slow manner. So, you can catch up, and you can now from there you can learn a bit more. From here you try to understand that okay, there are these concepts happening and which have high physical meaning, and you try to appreciate its formulation. Okay, what is Noether's theorem? So, I may not prove the theorem itself, but I will give some examples that is along with Noether's theorem and conservation and symmetries. And do not forget to link this thing to what you are learning in group theory. Okay? Group theory also deals with some kind of symmetry, some kind of change, transformation. So, I will also say what is going to happen. So, yesterday we said that we have a quantity S called action, which depend on x a and x dot a, possibly also time. Okay. Then we said that this is the quantity a system wants to minimize it. So it doesn't want to spend much of this item, this thing. It want to extremize this quantity. So that extremized thing will give the equations of motion. And when okay, so now I'm going to take an example of an action S, which is nothing but the integral of dt, a quantity called Lagrangian, and L is nothing but kinetic energy minus potential. Again, this is a function of and time. Okay. Now I am going to make consider a particle which having a kinetic energy, only kinetic energy. It doesn't have potential energy. Okay. And it is having a mass, so the kinetic energy is 1 by 2 mx dot square in one direction, x direction. Are you fine up to this point? So don't feel free not to take notes. So these things are everywhere in online, you can find all the notes there. So now you can try to look at what is going on here. Now I am going to introduce one thing. So I am going to turn my x to a new x, I call it as x prime, or I am going to turn my x to x prime with a constant. So what I do is that if you imagine a coordinate space, okay, a 2-dimensional coordinate, of course you can imagine 3-dimension. So this is x, y, z, and there is a particle here. Okay, and I am restricting its motion in a line, and it only has a kinetic energy. So that motion of a particle is given by this kinetic energy. Okay. Now what I am saying is that I am going to shift this coordinate to x to plus a. Okay, so instead here what I am going to do is I am going to place this object here and to have a motion. So this is my A. Okay, and this is constant. This is a constant shift, right? This is not a function of time. So do you get the picture, right? Now what I want you to do is that now it has a new x called x prime. Now the kinetic energy changes to a new kinetic energy, right? It becomes 1 by 2 m x prime dot square, right? And what is x prime dot? X prime d by dt. What is this? dx by dt is x dot. So okay, so this is x prime dot. Then this becomes t prime is 1 by 2 m x dot square, right? So what I want to show here is that so Lagrangian is actually t minus v. Okay, when I make the translation, this object didn't change. Is it confusing? No, because I said that my coordinates are changing like this. Okay, my coordinates are changing like this, and I have a particle moving with this kinetic energy, particle having kinetic energy, and I make a shift in this coordinate, and this is my Lagrangian, my potential is 0, so Lagrangian is actually kinetic energy T. Then I said that Lagrangian prime is equal to Lagrangian without prime. So actually the shift in this coordinate made this quantity invariant, like this quantity didn't change. That means my action is not changing even after making this translation. So this is called spatial translation, and when we have this thing, I will show that there is something interesting happening. Now let's rewrite our equation of motion, Euler-Lagrange equation, x minus d by dt of dou L by dou x dot equal to 0. Now I said that this is my Lagrangian is t, since my potential is 0, okay, and then my Lagrangian becomes 1 by 2 m x dot square. Okay. Now plug this Lagrangian here. What is this object? This object is 0, and what this object become t by dt of what? mx dot. So what I see from this equation of motion, d by dt of mx dot equal to 0. So what does this mean? Yes, exactly. So this part is constant of time. So this we normally call it as momentum p. Okay. So this is translation symmetry actually, and these kind of things nowadays have very importance in cosmology as well when we discuss shift symmetric scalar field, scalar tensor theories. So so what I did is that when we say that action is invariant on something, we will immediately find the consequence in the equation of motion. Okay, and that it is. So one more thing, when this is 0, when this object is 0, dou L by dou xa is 0, so then this coordinate xa is called cyclic coordinate. Cyclic coordinate, or it means that it's an ignorable coordinate. It can be ignored. Okay, so because on this coordinate, this there will be always a conserved quantity. Okay, so does this make sense? So if this is 0, if this quantity is 0, we have a Lagrangian. Okay. So from Lagrangian, if we find out that this is true, then this xa is called cyclic coordinate. So whenever we have a cyclic coordinate, there will be a corresponding conserved quantity that can be seen from the Lagrangian equation of motion. So you see that this is 0, that means time derivative of this object and is 0, that means this object is a constant in equation of motion. Yes.
So when you say that the conserved quantity, will it be always with the momentum, or it can be anything?
It can be anything. So that's why this quantity is more, I will define it. This quantity is called generalized momentum. So when I introduce Hamiltonian dynamics, I will say that one. So this linear momentum, conservation of linear momentum is only a consequence of this translation symmetry. Okay. So there can be a rotational invariance. So I can x prime with some matrix x. This is a rotational matrix. Okay, if I am considering a Lagrangian of an object which is rotating, and I say that I am going to change rotate my coordinates, and if that action or the Lagrangian is invariant on this one, again we will have a conserved quantity here. Yes, angular momentum, that will be an angular momentum. Okay. And I also want to give one more idea, conservation of energy. So I want to, yes, so this thing is called translational symmetry, okay. Why it is symmetry? Because even after making this translation, my action remained the same. So it's a symmetry, right? Okay. Symmetry means, yeah, already Manabendra introduced what is the idea of symmetry. How do we understand symmetry in an object?
Yes.
Okay, for this one, if I rotate like this, you are not realizing I am rotating this one, right? Because it's a symmetry. Okay, so now I want to say that one more thing. If the I said that Lagrangian can be a function of x, x dot and time. Suppose my Lagrangian is not depending explicitly on time. Yes. Okay, so let me write a bit more clearly. When I say explicitly, I want to write my Lagrangian xa. This coordinate is depending on time. This is a implicit dependence. This time dependence is explicit. Suppose my Lagrangian is not depending explicitly on time. That means that partial t is 0. So partial will be on this one. If I am taking exact differential in time, then I have to do this one, dou L xa dou xa dt plus, okay, this becomes exact, dou L by dou x dot d by dt of plus partial L by. Do you understand? You know this difference between this d and the partial d. So there is a difference. Okay. So when I say the complete difference, I have to do all these things. When I say it's a partial difference, it's only going to happen here. Okay. So my claim here is that suppose my Lagrangian is not explicitly depending on time, then what happens? So there is a quantity called h, which is x dot a dot l by dot x dot minus l is conserved. Okay. So how I'm going to show that? So you see that dh by, I take a time derivative, exact time derivative of this one, then I have to do a time derivative on this one, this double dot a dou L by dou x dot plus d by dt of dou L by dou x minus this L is like this. L is, I am saying that L is a function of x dot a, not explicit dependency on time. So this become dou L by dou x. So I am going to okay, here I all have a's here, x dot a plus dou L by dou x dot a x double dot, and minus sign will, here I will have a minus sign. You see that this is I said that there is a quantity defined to be like this. This will be constant in time in my of the system. So how do I do that? I take a time derivative of this quantity, and when I make a time derivative of this quantity, I said that my Lagrangian is not depending explicitly on time. Then I will have an expansion like this. If it is an implicit, then I will have a partial. I made it this to 0, right? So then these terms cancel, and yeah, here I have a dot. So this become x dot a d by dt of dou L by dou x. Do you know what is this? This is the Lagrangian equation of motion. So this will be always 0. Okay? So that means that this is 0. So it means that if there is a time translation invariance, so if my time is shifting, there is my system becomes invariant on that translation on time, and this quantity is called Hamiltonian. This becomes this is a conserved quantity. Okay. So now you have noticed that, okay, when I say that there is a invariance after making some operation to my coordinates, something is conserved. So that's so then there is a deep theorem behind it, which is called the Noether's theorem, which is so the consequence of Noether's theorem, that's what we are seeing here. Okay? Do you get the point? Yes.
But on this theorem, do you look at always at the Lagrangian or the action?
So Lagrangian is actually action is actually integral over Lagrangian, right? And there is a difference. You have always a total derivative term. The total derivative can be vanishing. Okay.
My question is, because in the action,
Mm-hmm.
you do have the time dependence because you are introducing it out.
Yeah, yeah. So yes, we.
But you are here talking about time translation.
Yes, yes. So the time is implicit depend on the coordinates of the configuration space.
But to talk about analytical generation, you are talking about explicit.
Yes, yes. Explicit dependence, I removed it. Yes. So
Then can you take action
mm-hmm.
to see the conservation of energy?
Yes, yes, I can take it, right? Yeah.
Is time still there in action? Is it not integrated outwards?
Time, I think there will be, so actually what we say is that the Lagrangian is not explicitly depending on time. So the action is not, because action is integral over time, right?
I think you should put clearly as a time translation in time,
Mm-hmm.
so that the Lagrangian is time independent explicitly.
Yes, yes. So what action is actually integral in time. So it's not an explicit dependence is not there in action. Yeah, yeah. So maybe what I write before the action here, action is actually, there is no time dependence here because there is an integral over time. So yeah.
That's why
You got confused. Okay, okay. That's a mistake. It's because I should not write action like this because here action, which is x dot t integration over time. So I integrate this object in time. So time is not having here. Yeah.
to find the symmetries, should we look at the action or the Lagrangian?
We should look at the action. Yes. Action should be invariant.
But action in that sense will always be independent of time.
That's true. Yes, yes. To understand time translation symmetry, we should look at the Lagrangian. So
What Noether theorem says? To look at the Lagrangian or
Lagrangian. We had to look at the Lagrangian. Yes. Yeah, yeah.
But yet you should write time translation, just like the space translation explicitly.
Explicitly.
Yeah, to make an analogy to.
I see. Okay. So how do I do it?
Something like x plus B or something.
Yes, so
That name doesn't change.
yes, I understood what you mean. So
It's just like you give chocolate to a older sister, you still give a chocolate to the younger sister.
okay, understood. So let me put a time to time plus a constant, okay? And I said that this is a constant, so change in time is a constant. So that means the change in time on the Lagrangian will be 0. Do you get the point? Does it make sense?
It makes sense.
Yeah.
That name doesn't change.
Yes. Yeah. So I think then there will be this quantity which is conserved. So like so like what Manabendra commented, like when we want the Noether's theorem talking about we have to look at Lagrangian actually to see the invariance to see the conserved quantities. Okay, so when we do the proof of Noether's theorem, we always look at the Lagrangian. So we make a symmetry to the Lagrangian, and we need to see the conserved quantity from the Lagrangian. Okay, that's why I'm using this L here. So this is, so I said that this is 0, right? In the time translation, I said this object is 0. So we are looking at the Lagrangian. Okay. Then from this equation, I understood. Okay, this is conserved because this is going 0. So actually, we are looking at Lagrangian. Okay. So this is the whole idea of Noether's theorem. So I'm not going to give the proof of this Noether's theorem. So I want to give you an impression that something is happening of this kind, like dou L by dou x is 0, then there is a quantity which is conserved. Okay, and if Lagrangian is not explicitly depending on time, then a quantity called Hamiltonian is also conserved. Now, the rest of the half an hour, I'm going to talk about Hamiltonian formulation. So this will be just to get some bites, not to have full understanding. Yes. So everything is just a bite, nothing. Okay, so now I want to introduce the Hamiltonian formulation. Hamiltonian formulation. Hamiltonian. Okay. Okay, so Hamiltonian, let's start from the Lagrangian equation of motion. Dou x a minus dou L by x dot a 0. So what? Okay, so why we need this kind of another formulation? So the idea is clear that it's about some technique to get the equations of motion. And in the first class I said that when we have a motion, when we have an equation like this, what we want to do is that we want to solve this equation. That's the aim of classical dynamics. So we want to know the trajectory of this x of the particle. So we want to get the solution for x. So since there is two derivative here, so this is a differential equation of order 2. We want to make two integration. Okay, we want to make two integration to get the equation of motion, provided that we give either initial condition or condition at two boundaries. So usually when we say the initial condition, we need to say that what is x at time 0, what is x dot at time 0. So without providing these two information, we cannot integrate it. Okay? So now this, for a complicated system, integrating twice is, it's getting highly complicated. If we have a system like a collection of particles moving and we want to know this equation, then we have to do the two integration, and also in this equation also we have to do, in the end what we get is this equation, right? An equation, suppose we have a Lagrangian t minus v and t is half m x dot square and v is minus 1 by 2 k x square. So this is simple harmonic oscillator. So if you put this Lagrangian to this equation, and we see that here this this becomes m x dot d by dt m x dot plus k x, and this is m x dot dot plus k x equal to 0. So what I want to show is that even with the Lagrangian formulation, we end up with the two differential equation of order 2. Okay. So Hamilton wants to remove this one. So what he did is that he promoted this quantity dou L by dou x dot A to, he said this is P, this is my generalized momentum. So this need not be linear momentum as we discussed, as we mentioned here before. So this is called generalized momentum. It can be linear momentum, it can be angular momentum, it can be. So this is called any definition is called generalized momentum. Okay. Now we had this configuration space. So we were talking about Lagrangian with the configuration space, okay, which is depending on the point is depending on x and x dot a. Now since we are introducing a quantity p, this becomes a new space called phase space, which a point depend on x and p. So this is called conjugate pair, okay, in phase space. So I said that there can be a trajectory in conjugate space will be again a some other trajectory in this phase space. So phase space is space of conjugate pairs x and p. X and p are called conjugate pair, and this is just x and x dot. Okay, configuration space is x and x dot, phase space is x and p. It's a conjugate pair. Now I will introduce Hamiltonian H. This is nothing but p q dot minus L. So again I am skipping one important thing here, which is called Legendre transformation. So how do you arrive at this H is actually a Legendre transformation x dot, okay, and H is actually a function of q, p and t. Okay. So this is the Legendre transformation. So it's a mathematical technique from one function to go to another function which has a new dependency. So, here new dependency is P. So, I introduce the Legendre transformation is like this. So, this is a mathematical technique, nothing beyond that. So, by implementing this Legendre transformation, I can define what is H. So, one thing you should keep in mind very thoroughly is that Lagrangian is a function of coordinates and its time derivative. Yes.
I think you have to choose which one to use between Q and X, otherwise it could be confusing.
Ah, that's true, yes. That's true. X and P, X dot. Okay. So that will be A. So, one thing you have to keep in mind is that Lagrangian is depending on coordinate and its time derivative. Hamiltonian is depending on conjugate pair X and P, and there is a, of course, explicit time dependence of time. Okay. Now, for convention notational and easiness, I am going to turn all my X to Q. So, I just rename it X to Q to make it easier. Okay. So, maybe otherwise I will again I will be mixing things here. So, QA dot, this become Q dot, so Q. Okay. So, Hamiltonian is a function of conjugate pair P and Q. Lagrangian is a coordinate Q and its time derivative. So, that's a clear difference. So, when given a Lagrangian using this definition, you can always define Hamiltonian like this. Now, there is a question here, there is a Q dot. How I am going to remove it? Okay, so all this Q dot has to be removed from this definition of this one, right? Okay. From this definition of conjugate moment, you have to replace it. Otherwise, it is not a Hamiltonian. If there is explicit dependence on Q dot, it's not Hamiltonian. So, you have to remove it. Now, I will derive the Hamiltonian equation of motion. So, there are two ways you can derive it. You can either from this definition, you can vary this variable, this h, and vary. So you have to vary this as well. Then you can equate right hand side and left hand side to get the Hamiltonian equation of motion, or you can plug into action principle, and because the Lagrangian is here. Okay, so you put Lagrangian in terms of Hamiltonian, then you make the variation, you will get the Hamiltonian equation of motion. So, let me do this dH. So, this is H and P is defined to be dou L by dou Q dot. Then dH is dP A Q dot A plus PA dQ dot A minus, this is Lagrangian. So, I have to do this partial derivative Q dot dt. Okay. So, I expanded this right hand side, and I know this dH from this left hand side, it's function of Q, P and T, it becomes dH by, okay, it's a partial dQ okay, plus dou H by dou P A PA plus dou H by. Okay. Now, okay, so here I think what is this one?
Last term should be partial derivative.
Ah, this is partial derivative. Yeah, this term is nothing but PA, right, from this definition. Now, what I have is some terms.
This will be del Q dot, I guess.
Q dot, yes.
Q dot.
Where? Here? Here? Okay, this is a, there is a dot. There is a dot. Here also there is a dot here. So now this is P, and dou L by dou Q. What is dou L by dou Q? Is nothing but P dot. Okay? So this is coming from Lagrangian equation of motion. So I said that my x are going to be q minus d by dt of dou L by dou Q dot, and I said this is dou L by dou Q is dot is P, so this becomes P dot. Okay. Now I have this on left hand side, with this replacement on right hand side I have it. So you collect the coefficients of dP and dQ, right hand side minus left hand side should be 0. Then the coefficients of this one and this one, dq and dp, you compare it, then you will see these equations of motion. PA is minus dou H by dou QA, Q dot A is dou H by dou PA, and by dou T is dou H by dou T. So these are Hamiltonian equations of motion. Now I said that as a motivation to study this Hamiltonian formulation, I said that from the Lagrangian equation, if you look at the equations of motion, you will have this form, x double dot is something, right? So you have to make a 2 integration, but instead what you see here is that in this formulation what we have is that 2 equations of motion with first one integral, right? So you don't need to take two integration, instead you take two separate integration, which is much more easier to do it. So to arrive at this, what Hamilton did is that he introduced this quantity P, and he said that P and Q are having same equal footings. You can say that it has equal importance, and he said it's a conjugate pair, and he found a space called phase space, okay, which depends on x and p. Then with the Legendre transformation he defined what should be that quantity corresponding to Lagrangian. He called it as Hamiltonian. Then by using symbol technique you can arrive at this equation, okay. So this is also a another formulation of classical dynamics. So and this also had many advantages, like if you want to study quantum nature of a system, so this is the way we have to go it. We need to know Hamiltonian equations of motion. From the Hamiltonian, and Hamiltonian has a physical meaning. It is something invariant on time translation. As time progresses, the energy remains same. So that's the relevance of Hamiltonian. And also it also has a relevance when you go to complicated theories like GR. To count degrees of freedom, you need a Hamiltonian formulation of system, like how many degrees of freedom are there. Suppose we have a complicated system and we don't know, from the Lagrangian point of view, we don't know how to count the degrees of freedom in a nonlinear theory. For linear theory it's fine, you can do it from the Lagrangian. For a nonlinear theory you have to go to this Hamiltonian description to count the degrees of freedom, to count the constraints, and to get the final number of degrees of freedom. And what else? And it's also give a path to quantum mechanics. So something I missed, maybe I stop here at this point, and I want to say that I didn't cover one important aspect in classical mechanics, a technique called Poisson bracket. So Poisson bracket, just it's a important tool to get the equations of motion. Okay, so Poisson bracket is also important to move to quantum mechanics, to formulation of quantum mechanics. So these are the things which are important in learning classical mechanics. So this list doesn't stop. It comes with phase space, then Hamiltonian, then Poisson bracket. So if you have all clear understanding of what is this, and if you know really how to do things, next thing is to study the system. So when studying system there will be complications, so you have to clearly make sure that all these things are correctly defined. When you do the system, when you try to solve the system, then you will get the correct answer. So with this tool you can cover all the classical mechanics, including electrodynamics, classical field theory, everything. The tool is this one. This is the toolkit. Okay, and to understand this toolkit, okay, there are some conceptual changes we have to make, like configuration space, phase space, idea of Lagrangian, idea of principle of least action. You can think this as a toolkit. If you have a good control over all these things, then you can do smoothly all the classical things in the world. Yes, with this I stop. Yes. Yeah, so if you have some questions, yes, please.